I definitely wouldn't take max. That's all I'm going to say. If I wonder like what we're talking about, it's like recorded. Okay. Anyway, you know piecewise functions. Yes. So we have like a love-hate relationship with piecewise functions. Just a quick recall. We're not going to do one right now, but a piecewise function, the ones look like this. And like, 2x when x is bigger than 1, and like 5 when x is less than 1 or equal to. Remember these? Yeah. We're going to get into them a lot after this section, actually, but I'm going to do this section first to kind of like ease our way in. So, in general, piecewise functions are basically just saying, this is what the graph should look like when x is bigger than 1. So when x is bigger than 1, I should have the line 2x. And when x is less than or equal to 1, I should have the line 5, which is a horizontal line up at 5. And remember, one of these is open, one is closed. If it's greater than with no bar, it's open. If it's with the bar, it's closed. So like there's your piecewise function. 3, 4, I think that's right. Right? No?
The equation does show 5 when x is less than or equal to 1.
Yeah.
It's a constant.
So it just means that y equals 5, the line 5, when x is less than or equal to 1, and the line 2x when x is bigger than 1. So that's a piecewise function. I know that you done them in algebra too. But did you know that all absolute value functions are really piecewise functions? They are. It's true.
Thank you for making my life complicated.
So that's the lesson, right?
Yeah, right.
That totally
So think about it.
didn't get any.
That
it wasn't pointed over there.
Oh, well, that's all right. Alright, so y equals the absolute value of x is a v. Looks like that. And these are actually two different functions. Whenever a function takes a drastic turn in a different direction, it's usually piecewise, or its absolute value, which is really piecewise. Because regular functions just don't do that. They don't like go in one direction and like flip into a different direction, or have a corner like this does. So that's kind of the clue that it's a piecewise function. Let's think about what these two parts are. This part on the right is the function what? Y equals x. But the function y equals x goes on forever, and it would continue down that way. It would be forever where like the black and the green are. But that's not what the absolute value function does. It pops up over here. What's this equation? Y equals negative x. So the absolute value function is really a piecewise function. The two parts are, it equals x when x is greater than what? 0. And it equals negative x when x is less than 0. There's one more thing to put there, but hold on. So does that make sense? When x is bigger than 0, my function is y equals x. When x is less than 0, my function is negative x. They meet up here. It's not open there. It is closed, so I should make one of these equal to. I can't make them both. Why can't I put a equal to sign on both of them? What would that make it not be? A function. It wouldn't be a function if I make them both equal to, because it means like this place would be filled in twice, both by this part and by this part. So it can only be there once, but it can be in either part. Okay. So this absolute value function is really just a piecewise function. So is this. But this absolute value function is easy to graph because I know it's a v, and it behaves like other functions where like a +2 moves it to the left 2 and a +1 on the end moves it up 1. This is like weird. I wouldn't know how to graph this, but if I write this as a piecewise, then I can graph it, and that's what we're going to do. So I'm going to kind of explain how this gets written like this without knowing what the graph looks like. Let's say we don't know what the graph looks like. I've never seen what that graph looks like before, but I write it as a piecewise, and when I have it piecewise, I can graph it. What I do is I take my absolute value bar, and I figure out what would make the thing inside equal 0. Well, in this case, it's easy. What number makes that 0? 0. I make a number line, and I partition it at 0. Good job. I make a number line, and I give myself a spot at 0, and then I test. I pick any number on that side of 0, and I plug it into the absolute value bars. And if I get a positive result, I take the absolute value bars and I drop them into parentheses, and I leave it alone. So when I plug in a number bigger than 0, like 2, since it gives me a positive number in there before I've ever absolute valued it, since I get a positive number in there, then I drop the absolute value bars into parentheses and I leave it alone. When I plug a number less than 0 in, like -3, if I plug -3 into here, I have a negative number inside the bars. So now I drop the bars to parentheses, but I change the sign. And those two pieces are the pieces of the absolute value, or of the piecewise function. When x is less than 0, that's my function, -x. And when x is greater than 0, that's my function, x. Get it? I don't expect you to get it first time through. So we gotta try this a little bit harder so that it'll make some sense. Okay. If we want to write this, we're going to pick where are the places that make this 0 and make this 0? -2 and 1. So I'm going to split my number line into -2 and 1. When I put that on the number line, how many, I'm going to call it partitions. How many partitions do we have? 3. We have 3 places to test. Therefore, when I make the piecewise, I'm going to have 3 things happening. I'm going to have 1 when x is greater than 1. I'll have 1 when x is between -2 and 1. And 1 when x is less than -2.
X is greater.
So, first, does that make sense? It's just a lot of steps, but it's not that any of them are hard. So, pick the places that make the absolute value bars, the stuff inside, equal to 0. Put those 2 numbers on your number line. It could be 2, it could be 1. It's rarely ever 3. And realize these are the 3 partitions I need to talk about. I need to talk about when x is bigger than 1, so it's this part. When x is in here, between -2 and 1, that's this part. And when x is less than 2, that part. Okay. First I'm going to do this, I'm going to go positives first because it's usually the easiest, and then I'll work backwards. So pick any number bigger than 1. It doesn't matter what you pick. Any number bigger than 1 is going to give you the same result. So let's say I pick 3. When I plug 3 into here, do I get a positive or a negative? Positive. I get 5. So x plus 2, I drop the absolute value, change it to parentheses, and leave it alone. And when I plug 3 into here, I also get a positive. So I drop the absolute value, change it to parentheses, I leave everything alone. The sign in between them I leave alone, I just keep it just as is, except the bars become parentheses. And then I can reduce this. So algebraically, this negative would distribute. So I'd get x plus 2 minus x plus 1. What happens to the x's? They cancel, so I just have 3. It's just a coincidence that I had picked 3 as an x value to use. What this is telling me is the function is going to look like y equals 3 when x is bigger than 1. What I have once this is reduced is the function for when x is bigger than 1. I put it into the piecewise part. Okay, now pick a number in between -2 and 1, and now you'll see what happens if the sign in the bars is different. So let's say I pick 0. 0 plus 2 is 2, so that's fine. The absolute value bars change to parentheses, and I leave it alone. Now, when I pick 0 and I plug it in, I get a negative in those bars. 0 minus 1 is -1. So this means I still change the bars to parentheses, but the sign in front changes. So either you can just change this minus to a plus, or put a negative out front because the minus and the negative will become a plus. Do you know what I mean? So I'm changing it from subtraction to addition, or to minus a negative either way. So what I really have here is x plus 2 plus x minus 1. Bless you. If I put it together, 2x plus 1. So the function y equals 2x plus 1 is what's happening when x is between negative 2 and 1. Aren't you glad you came to school today? Now we're going to pick a number less than negative 2. So like negative 3. You can kind of predict what's going to happen. When I put negative 3 into here, I get a negative. So my bars become parentheses, but I change the sign in front. Negative 3 in here gives me a negative, so I change the bars, but what sign should be in front now?
Plus.
Either minus a negative or a plus, either way. So I've got negative x minus 2 plus x minus 1. And what do I get in the end there? Negative 3. So negative 3 is the function when x is less than negative 2.
That wasn't too hard.
Is it a coincidence that you got 3 for the first one?
It like 8 times out of 10 is going to work that way. It doesn't always, but a lot of times, yeah, it's going to work that way. Now you got to graph it. Questions so far? Yeah.
When you distribute the negative, wouldn't it be plus 1?
It would be, see, because I'm changing the sign out front, I'm really making them addition.
Yeah.
Yeah. That's okay. So let's graph it. I know that negative 2 and 1 are my big, changing points. So when x is bigger than 1, I have the graph y equals 3. What does y equals 3 look like? Horizontal line, right? Up at 3. So when x is bigger than 1, I've got this going on.
It's open.
I'll say that in just a second. You'll see what happens. When x is less than negative 2, I might as well skip to this because it's so easy. When x is less than negative 2, I've got it that way, and it's a horizontal line at negative 3. And then I got to get this inside part going on. This is a lot of information at one time, so I know it's a lot to take in. But if I want to figure out what's happening at negative 2 and at 1 for this part, all I have to do is plug in these endpoints. If I want to know when x is negative 2, where am I starting for this part? Put negative 2 in. Well, negative 2 times 2 is negative 4, plus 1 is negative 3. Oh, cool. At negative 2, I can start actually right there, where I ended on the horizontal line. And if I finish, when I plug in 1, 2 times 1 is 2 plus 1 is 3, I finish here for that. And I know that it's a line, so I basically can just connect it. Oops.
Whoa.
Yeah.
That's pretty cool.
Yeah. Wait.
Do you just plug in those two numbers?
I do, because I know this is a line. I plug in the last one and the first one, and I know it's a line, so I just connect them. But you could also say, the slope of this is 2. So from here, I'm up 2 over 1, up 2 over 1. It also gets me to the end, depending on how I want to do it.
But doesn't it?
What if they don't?
Okay. When they're like this, they're always going to connect. When they're fractions, they might not connect. And we're not going to do fractions today. It's going to take us a little bit of time to get through. So, yeah. Right now, they're going to always connect. So as far as our equal to's, we can put them in wherever we want once. So with the 1 and the 1, I can put it once wherever I want, and the negative 2 and the negative 2, put it wherever I want. I'll usually just put them here and here. Put it equal to once, because it does all equal each other. It is continuous. It never stops. What do you think?
Easy. It's not that bad.
Okay. Let's try 1. It goes a lot faster when you're doing it yourself because you don't have to explain all the steps. It's just a lot to explain.
So we're trying to.
So yeah, just try it and see what you get with it. And it's really hard to hear something on the first try and be able to do it. Yeah, I'm going to stop the video.
Are we